All right, recording is rolling. It is Monday, September 9th. Of course, I haven't seen you guys in a few days. I really don't like this in school, so sorry about that. But I hope you guys made a good use of the time for the last few days of school. And so let's look at top scientists for linear motion. I think I'm going to use this video for all my classes. So here's all my top scientists for honors. This is if you did really well on linear motion. I haven't handed back linear motion quizzes yet. There's still some late quizzes I got to get on, but as soon as I get them, I like to get those quizzes back to you guys as soon as I can. Right? But I got to get them all in first. Right? And for my other classes, AP had their own type quiz. They have the hardest quiz, their AP. There's also a conceptual quiz, and I got some students that did pretty good there too. So if you're in any of my top scientist lists, then awesome job, top scientists. Oh, right, projectiles. So yeah, we're going to go into projectiles today. I have this projectile puzzle that is pretty all-encompassing, and we're going to take most of today to look at that and analyze that. I think if you can understand this one, then you'll be able to get pretty much anything I throw at you. We'll look at the posters that most of them I posted back on Friday. I was directing you guys to look for it, so we'll look at those a little bit closer today. Tell you guys about, I want to take you guys outside for a lab tomorrow. We're going to take these launchers and launch some little bouncy balls and do a projectile lab based on that. Tell you guys what's going on there. And projectile puzzles. Back on Friday, the sub should have given you guys this page. They asked you guys before I hit record. You guys said you had this page. I do want to solve these with you guys. We won't have time to get this page yet today. Tomorrow I want to do the lab, so maybe Wednesday I'm thinking I'll be able to solve a bunch of those with you guys. And if we're making pretty good pace, then I do want to pick that page up from you by Friday. So let's see. Wednesday, Thursday, you can solve some. Yeah, okay. All right, and then for my AP students, they also have an AP classroom that I want to go over with them on Friday. So done by then. And then most of the questions I thought were pretty straightforward, except for 15's a pretty challenging puzzle. So I want to give them a heads up on it. All right, so you guys good with the agenda? What's going on? Oh, you guys all have notes out. Oh, I see notes out. You guys got notes out. You guys got paper, notes. All right, because it is projectile time. We're going to solve this right here. So here, I wrote the questions out long form. We'll take a look at this, and then I'm going to redraw this with you guys. All right, as you guys are getting your notes out. You guys get notes out. There's also some paper on that desk in the back if you need some paper. Okay. So here's the scenario. I got a cannonball blasted at 50 meters per second at 37 degrees above the horizontal on a long flat plane. There you go. Cannon. But oh, look, it's pow. There goes the cannonball at 50 meters per second. There's 37 degrees from the horizontal, and then long flat plane. But because there's a gravity field, it's going to pull back down. It's going to crash land way down here somewhere. Okay. I got 3 questions. What's the hang time of the cannonball? That's the total time that it's in the air. So from the blast point to the crash point, what's the total time? Right? What's the maximum height of the cannonball? Hey, what's this maximum height right here? How high does it go? Okay. And what's the horizontal displacement? That's to say, how far downrange does the cannonball land? Okay. So we're going to answer all those questions. Okay, so you guys good with that? Okay. So I'm going to take this off, but then I'm just going to redraw this whole scenario. All right, so here we go from scratch. Okay. So scenario, blast, cannonball, 50 meters per second at 37 degrees above the horizontal. Okay, we'll shorten form of that. All right. 3 questions. What is the hang time? So call it T hang. 2, what is the maximum height? Call it H max. 3, what is the horizontal displacement? I'll just call it X. Okay. And again, here's the long forms of all those questions, and then here's the variables and how they match up. Boom, 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 just like that. All right there. All right, so 3 questions. Question, question, question. Okay. All right. You guys all got rulers on your desks? You guys got rulers? All right. So turn your notes, landscape, and let's make a line that's 24 centimeters long. All right, I'll try to some space here. maybe leave a little margin at the bottom like I'm doing too. This will help you out. Okay, so going for 24 centimeters. 24 centimeters. Bam. All right, you guys got a 24 centimeter long line. Now I'm going to put some dots on this line. So let's go at the 0 centimeter mark, and then every 4 centimeters, put a dot. So 4, 8, 12, 16, 20, and 24 centimeters. So we should have 7 dots. There's a specific reason I chose these numbers, 50 meters per second and 37 degrees. It's going to work out really nice for this particular question. Okay. All right. At the far left dot, let's draw a little cannon right there. Draw a cannon. It's going to be angled up at some angle. We'll call 37 degrees. It's going to blast a cannonball. Okay. Now the cannonball is going to follow a parabola path. And let's say it lands on the very last dot, which means, do you guys think right in the middle, that middle dot, do you think it'll be at its maximum height point? Maximum height point? Okay. So we'll go to that point, some distance up, do something like this, and see if I can draw a pretty well parabola that peaks right at the middle there. See what it does. All right, I think that'll be pretty good. That's a pretty good parabola. Boom, just like that. Right. Here's the path of the cannonball. Right, you guys got a parabola in your notes? It's about like that. Okay. All right, guys, a moment there. Catch up there. All right, everybody getting. Go. You guys got paper. You guys got paper. All right. All right. Okay. Now, back at the point of the cannon, okay, let's go ahead and draw a velocity vector. Right? Do you guys notice I'm holding my ruler flush to that parabola curve? If you drew okay, hopefully you drew it about like this. Right? So I can draw a velocity vector and call this V blast equals 50 meters per second. Okay. Got a blast speed, 50 meters per second. Okay. Now, what I do is I'm going to take a snapshot. I'm going to take a picture every second, as it turns out. Okay. So one point's going to be right at the point of the cannon. So go ahead and draw like a cannonball, like as if you like zoomed in. Right. The cannonball could be leaving the cannon barrel right there. Pow. Right. Then every second, the cannonball moves in equal horizontal displacement. Right? What you'll see is, as we go through this analysis is that, guys, do you think gravity pulls horizontally or vertically? Gravity only pulls vertically, right? Gravity only pulls down. Gravity doesn't pull horizontally, right? And we've been ignoring air drag. So is there any reason then that the ball would be speeding up or slowing down horizontally? No, right? So it'll be going equal distances in equal time intervals horizontally. That's what these dots are for. So above every one of these dots, draw a location of a cannonball on that parabola curve. So after 1 second, the cannonball could be there. In 2 seconds, in 3 seconds, it's going to end up here. All right. Again, I'm kind of working backward from knowing what the answer is, but this will make sense by the time we break this whole thing down. Okay. Cannonball there, and then at the last second, it's like right above the ground. It's about to crash land. It's about like that. Okay. Get this right. My best job here. Okay. All right, you guys good so far? Okay. Now let's draw velocity vectors for all these individual cannonballs. We got it for the first one. We got 50 meters per second. You guys think that as this cannonball is moving along, it's going to slow down a little bit, Right? I'm going to represent that by drawing slightly shorter and slightly shorter velocity vectors. Not crazy shorter, but just slightly shorter. Okay? And you guys notice again, I'm holding my ruler flush to that curve. See how it's flush to the curve? Or like a tangent line type sometimes for that term, right? So now I'm going to draw a velocity vector that's a little bit shorter than before. Right? And then the next one, so the next snapshot, right? Again, my ruler is flush to that curve right there. Right? Draw a velocity vector that's a little bit shorter than before. At the very top, ooh, guys, at the very top, do you think the ball's moving exactly horizontally just for that instant? And so I'm going to draw the velocity vector going exactly horizontally. Horizontally. Ah, that's just like that. Now it's going to start falling back down. Do you think it's going to go faster and faster, faster all the way down? So flush to the curve. The cannonball is picking up a little bit of speed right there, going a little faster. And this one, flush to the curve. Right, going a little bit faster. And then here, coming in for the crash. It's about to crash land right there. Wow, that's pretty good. Pretty good. Right? Bunch of velocity vectors, right? So remember the direction of the velocity vector tells you the direction of motion. The magnitude of the velocity vector, in fact, they're getting a little bit shorter on the way up and then a little bit longer on the way down, tells you the speed. Okay, you guys got those? Let's break those into components, because here's why. When we're making sense of projectiles, you're going to have to juggle two different dimensions. There's no new equations going on, but there is vertical versus horizontal. So we're going to have to say, well, how fast is the ball going across the field, and how fast is it going strictly upward? We're about to tackle that question right here. So at the blast point, 50 meters per second at 37 degrees from the horizontal, it's going kind of across and kind of up. So I can break that into components. So it looks like this, across and up. Right? I can do that for every one of these. I can break these into components. So how fast across the field, how fast up, or later on, how fast down. Ooh, could do something about like that. Okay. And then, so I'm making a bunch of little triangles right now. I'm going to go ahead, go back and put little arrowheads on these to represent vector components. So here's how fast across and up initially. After 1 second, here's how fast across and how fast up. How fast across, how fast up. How fast across, how fast down. Ooh. How fast across, how fast down. How fast across, how fast strictly down. Okay. Yeah, so we're separating out the vertical and the horizontal motion. We'll look at each one independently. Okay. Because like I was saying before, and you can see that right here, that guys, horizontally, what do you notice about the velocity in the horizontal direction all the way across? It's the same. It's the same. Right? If you drew yours exactly correctly, then it should work out like that. Right? You see how this is the same as this? Yeah, it's the exact same horizontal velocity all the way across, or horizontal component of velocity. Right? But vertically, it's a different story because gravity pulls vertically. So do you guys see, vertically speaking, it definitely gets shorter on the way up. It's zero vertical at the top, and then it gets larger and larger and larger on the way down. You see that? Is that? All right, you guys ready to put some numbers? Ready for some numbers? All right. So, oh, I need to throw an angle in here. Let's call this 37 degrees. I don't think my picture's 100% to scale, but you guys get it. That could be, let's say it represents 37 degrees. Okay. All right, we can go back a few weeks in this class. We haven't talked about this in a while, but I bet somebody remembers. How do you figure out how fast it's going across? Like, what is this component, this horizontal component right here? Does anybody either know the number that I need to write or how to get it? Does anybody know? Yeah, so we're doing sine and cosine, right? Sine and cosine, right? So some trigonometry, right? Right. I'm going to label this v sub x. This is going to be the velocity in the horizontal direction, v sub x. Okay? And here I'm going to do a calculation up here. So I'm going to do a little thought bubble up here. Right? So v sub x, that could be equal to, take the full blast speed. Well, here, I'll just write in the number 50. The full blast speed, 50, meters per second, and multiply by what? Sine or cosine of 37 degrees? Show of hands. Who thinks the one that's adjacent to the reference angle is cosine? Who says cosine? Ah, cosine of 37 degrees. Let's get a number for that. Right. Or maybe some of you guys know where this is headed before I punch this on the calculator. 50 times cosine of 37 degrees. Right. Guys, why did I pick 37 degrees? Because I'm setting up a what triangle? A 3, 4, 5 triangle. I bet it's going to be like a 4/5 ratio, something like that. Let's see if it is. Aha, 39.93. I'll call that 40. 40 meters per second. What if I didn't pick 37 degrees? What if I picked 36.87 degrees? Oh, well, now it's even better. 39.9999. Okay, so 40 meters per second, right? So back down to here, v sub x equals 40, and then the unit is meters per second. 40 meters per second across the field. Is that all right? Here, maybe I should switch to pink ink just so separate out the ink colors a little bit here. All right, guys, 1 second later, how fast is it going across the field? 40 meters per second. 1 second later, how fast across the field? 40 meters per second. At the very top of the trajectory, how fast is it moving altogether? 40 meters per second, because it's only going across the field. And that number hasn't changed. You guys think I can just fill in the rest of these? 40 meters per second, 40 meters per second, 40 meters per second. Yeah, it's always going 40 meters per second across the field. Right. I like to say too is, what if you were up in a hot air balloon? Here's a hot air balloon, and you're looking down on this whole situation. So here's my hot air balloon. I'm looking down. Right. Now, the point of being up in a hot air balloon looking down on the field is that you're not getting a sense so much of its vertical motion, but you are seeing its horizontal motion. And from that point of view, do you think way up here in this balloon looking straight down, it looks like it's going pretty much constant speed across the field? Yep, it's got 40 meters per second all the way across the field. That's what you see in that hot air balloon. Okay, you guys get there? Okay. Okay, so that was horizontal. Let's switch over and think about what's going on vertically. Okay. So, now vertically, remember, it's going to be a little trickier because as soon as this cannonball leaves the cannon barrel, do you think gravity starts to act on it? Right, vertically speaking. Right? So its vertical motion is always changing. Right? Its vertical velocity is always changing. Right? I'm going to label this initial component here velocity initial in the y direction. Notice this gets 2 subscripts versus in the horizontal direction, just 1 subscript was fine. Right? Because in the horizontal direction, well, that never changes, so I don't have to worry about it. But in the vertical direction, got to be a little bit careful, because how fast is it traveling vertically? Well, that's really only true for any one instant in time. Okay? Let's do some trigonometry here. Velocity initial in the y direction equals, okay? Guys, how can I calculate that? We start with my 50 meters per second full blast speed, but then multiplied by what? Sine of 37 degrees. That's it. See, what is that? 50 sine 37 degrees. Oh, look at that. That is 30 meters per second. Okay. So go back and label this 30 meters per second. Number 2. Right. Oh, hey, I mean, maybe you figure that out from the triangle geometry anyway, because 30, 40, 50, does that reduce to 3, 4, 5 ratio? It's the same ratio, right? Right. Because whenever I pick a 37-degree angle in a right triangle, I'm probably setting that up. Okay. All right. Well, if it was initially traveling strictly upward at 30 meters per second, how about this? How about this? Right? What if you stood next to the cannon and you just threw a ball straight up at 30 meters per second? Right? It's going straight up, and it's like it's slowing down, and it's slowing down, and it's slowing down. Right? There's some height. Right? So if I threw the ball straight up at 30 meters per second, how fast is it traveling after 1 second? Huh? It changes by 10 meters per second every second. So 20, right? 20, okay? So it's down to 20. Okay. This is 20 meters per second, strictly upward. Okay. Then 1 second later, how fast is it traveling strictly upward? About 10 meters per second. Then 1 second later, how fast is it traveling strictly upward? 0 meters per second. Okay? Because you guys know that gravity field is 10 meters per second squared downward. So if you throw a ball up at 30 meters per second, every second it's going to lose 10 meters per second. So 30, 20, 10, 0. Okay? And then the ball's going to start to fall back down. So from the peak point, after it's been falling for 1 second, how fast is it picked up to? 10 meters per second. And then after another second, it's up to 20 meters per second. Then after another second, it's up to 30 meters per second, just strictly in the vertical direction. Is that? So that's what we've been doing the last couple of weeks. Right? Goes hand in hand with those kinematic formulas too. Right? Like here, this one right here, this is what we've just been doing. Right? I threw it up at 30 meters per second. I was pulling down at 10 times however much time. Brings us to 20, 10, 0, 10, 20, 30. Well, yeah. Got the negative signs. Okay. Tell you the direction of motion. All right, so you guys good with that? All right. So yeah, so I want you guys to see the big picture of that. Now we still have to answer these questions here, okay? And then maybe tie this to something more generic. So what if we don't have really nice numbers? What if instead of 50 meters per second at 37 degrees, which works out really nicely like this? Right? What if it was like 23 meters per second at 14 degrees? Can you figure out all these questions too? Right? And then maybe you could just use the formulas at some point. Right? And I want you guys to see later on in class that these are going to tie back to those formulas. That'll also be true. Okay. So, sorry, question number 1. What is the total hang time? So from the point that the ball is blasted from the cannon to the point that it lands on the field way down here, how much total time is that? And this particular question, I think you might be able to stand back and just look at what we've drawn, and some of you guys might be able to answer that already. Okay, guys, who knows? From this point to this point, so the whole hang time. Guys, what's the full hang time for that cannonball? Huh? How many seconds? 6. You guys are saying 6? Because here's time 0. 1, 2, 3, 4, 5, 6. Ah, there's 6 seconds right there. Is that right? So the answer to this question is definitely 6 seconds. But let's go ahead and tie that back to the formulas. And I want you guys to see that it's also true. Right? Now, there's more than one way to solve this with the formulas. I'll show you guys at least a couple of ways. Right? One way is you can split this problem in half. That's what I like to do with a lot of these projectile puzzles, is to split them in half, right, and solve it halfway. Right? Guys, if you split this in half, also think about, actually here, let me back up a little bit. Back up here. I want you guys to see how all the variables connect generally, right? And the fact that we're going to be kind of routed into thinking about gravity and the vertical situation to solve this anyway, right? Guys, what if you do this? What if you turn gravity off? That's a good thing to be able to think of in this class. Can you turn variables on and off? How does that affect a puzzle? Can you turn variables up or down? How does that affect things? What if you turn gravity off? Guys, if you turn gravity off, what would this cannonball do? Yeah, fly off in a straight line into space forever. It would just fly, right? It wouldn't bend down at all. Right? And what if you had like weak gravity, like on Mars? You think of probably stay in the air a long time, go a long way, right? And then, okay, we're back to Earth gravity, right? So here's Earth gravity right here. Okay, so if I have some kind of time constraint, I know that's going to be related to Earth gravity pulling on it, which is something to do with its vertical motion, right? In fact, how many of you guys think that the hang time for this cannonball is exactly the same as for the ball that I just threw straight in the air. How? You guys think they had the exact same vertical motion? Yeah. So answering one would answer the other. Right? And that sounds a lot like a question that I threw at you guys back about a week ago, right? Which is, if you know how fast you throw a ball up, say, well, I guess in this case, like how much time would it take to reach the peak, right? That's what we're going to do here. So I'm going to set up the second kinematic formula. Final velocity in the y direction equals initial velocity in the y direction. Let me say minus gt. You guys see this is just a modified version of the second kinematic formula, right? So if I call up positive, then initial velocity in the y could be positive. But then gravity would be pulling down, which would be negative. That's why I went ahead and said minus gt. Just took care of the negative right there. You guys see that? Where I'm getting all these bits from? This is just a version of the second kinematic formula. I'm going to let the peak velocity go to 0 meters per second, and therefore solve for half of the hang time. And then later on, I can get the full hang time by just doubling that number. So see if you guys are following. Guys, how fast is this ball going strictly upward initially? What number goes right here? 30 meters per second. Wasn't initially being thrown strictly upward at 30 meters per second? And we got that from 50 sine 37, right? This is 30 meters per second, strictly upward. I'm just focused on vertical motion. That's all I have, just vertical motion. Minus, I got 10 meters per second times, okay. Now I'm gonna throw a subscript on this t. Guys, if you're keeping track, this t only counts from here to here, or if you like, from here to here, okay? Is that true? So that is half of the total hang time. So I can use this equation to solve for that, but then if I want the full hang time, I have to double that later. You guys get that? Right. Not the only way to solve it. I'll show you another way later. Right, so add that over 10 t half equals 30 meters per second. T half is 3 seconds. Okay, so it took 3 seconds to reach the peak. Hey, it took 3 seconds to reach the peak. Do you think it takes another 3 seconds to fall back down? Aha! So the full hang time is twice, well, that half hang time. 3 seconds goes right there. The hang time is 6 seconds. All right, that's what we were saying it was before, just by counting the frames. If we went frame by frame, it's like, okay, times 0, 1, 2, 3, 4, 5, 6, bam, right, 6 seconds, it's back hitting the ground again. Okay, and that's what this method is saying too. But now we have a more procedural way to get to it, more methodical way. All right, you guys good? Notes? Right. I'll show you guys a different way to do it, because if you know lots of different perspectives, then now you have some options. You have more tools in your toolkit. Right? Show you guys a different way to do it. What if I think about it this way? What if I go from the beginning point to the end point, and I look at this not in terms of velocities, what we just did, but in terms of displacement? I'll say vertical displacement. Guys, what is the vertical displacement from the ground back to the ground? What's that difference? Zero difference. You guys see zero displacement from the ground to the ground? Right? And if I just focus on the vertical motion, that's zero vertical displacement, I can use that second kinematic formula. It might look something more like this. I'm going to take this generic x and I'll change it into y for the vertical direction. So y equals v naught y t, and I'll say minus 1/2 gt squared. Because again, if up is positive and gravity's pulling down, it's negative. Okay, so I'll just go ahead and throw the negative right there. Take care of that already. Okay, is that? Okay. Okay. So that could be its height in general as a function of any number of seconds that have ticked along. Right? But I'm going to plug in a specific displacement, vertical displacement, which is 0 meters. Because again, if I'm going from the blast point, which is at ground level, to the crash point, which is also at ground level, that difference is 0 meters. That's where that comes from. Right. Guys, what number goes? Bam, right there. 30 meters per second. Because initial, this is velocity initial in the y direction. So initial in the y direction, was 30 meters per second. Is that? Okay. Now, I don't know this t yet, but you know that. Okay. Minus 1/2. Now gravity's pulling down at 10 meters per second squared, and then t squared. Okay. Okay. Different way to think of this. Right? Okay, guys, right? Now, normally when you use the first kinematic equation, solving for t, you'll kind of run into quadratic formula. You guys see that? Right. But we can skirt around that. Because it's equal to 0, I can just factor this out, and that's a lot faster to solve. So I'm going to do this way. 0 meters equals 30 meters per second. Half of 10 is 5 meters per second squared times t. And then factor a t out. Right. See, the advantage of doing this way is if I have two things multiplied together and it zeroes out, then if either bit is 0, the whole thing is 0. Okay. So if t is 0, then that would correspond to 0 meter. Hey, that makes sense because if at time 0 the cannonball is just leaving the cannon barrel, yeah, that is at 0 height. Yeah, that's true. Right. I'm more interested in this one right here. Right. So this whole inside expression to be equal to 0, because this is the actual full hang time. That's what that represents, the full hang time, okay? Which is some number of seconds down the road. Okay? Aha! And I bet you guys can see it now. If 30 minus 5t is equal to 0, add 5t over, divide by 5, and then a bunch of units. Guys, what's the answer? 6, and then if I kept my units, meters per second here, meters per second squared here. This is seconds. Yeah, there you go. 6 seconds. Okay. Which, we've known all along. First by just counting the frames, and then by using the velocity equation. Now we got a displacement equation. Okay. But it's all telling the same story. Okay. I want you guys to see it. Yeah, there's lots of ways you can work this puzzle out. Okay. Lots of tools for your toolkit here. Okay. All right, you guys good? All right. Right, so there, we just answered that first question 3 different ways, and there's other ways you can do it too, right? But there's 3 different ways to do it. Okay. Look, you guys ready to move on to this next question? H max. So how high does the ball go? Now it's definitely still a vertical question, right? Gravity is still going to matter. Right? We got to figure out how high does the ball go. Right? So, I bet there is more than one way to solve this one too. I'm going to solve it 2 different ways with you guys. Let's go equation shopping. If you want to solve for maximum displacement, what do you guys think? First, second, or third? I'll tell you what, there's only one you can't use. Which one can you not use? Yeah, the second one, because the second one doesn't say anything about displacement. Velocity, acceleration, time. If we want displacement, we're never going to get it out of that one. Yeah, so I'll solve this using both the first and the third, 2 separate ways. Okay. So H max, I could do, I'll go x equals v naught t plus half at squared, but I need to modify that for this particular one. Okay. So I'm going to say h for general displacement. Now it's vertical height change. It equals v naught in the y direction times t. And then instead of plus half at squared, I'll say minus 1/2 gt squared. So it's the same form. It's just a modified version. Is it? Boom. Like that. No, I'm solving for the maximum height, H max. So that's my question. Oh, it looks like this is set up to solve it. I wonder if we can just pop these numbers in. Okay. Ooh, I know initial velocity in the y direction was how much again? 30 meters per second. Goes right there. Guys, for how much time is going to take from here to here? How much time is that? Huh? 3 seconds, right? 3 seconds, right? We saw that a few ways earlier. Right? So, hey, I could just run this height time equation for 3 seconds, and wherever the ball is at the 3 second mark, that will be the maximum height point. Hence, it'll answer the question. Minus 1/2, got 10 meters per second squared, 3 seconds squared. Okay, just like that. That should take care of it. H max equals 90 meters there minus, ooh, guys, what's 3 squared? At 45, half of 10 is 5, or sorry, I'm so sorry. 3 squared is 9. Half of 10 is 5. 9 times 5 is 45. That's what I meant to say. 45 meters. Okay. Right, so there we go. Okay. That's how high the ball goes. 45 meters. Again, to show you, there's more than one way to solve these. Okay. What if I use that third kinematic expression instead? So let's try that one out. So I'll go final velocity in the y direction squared equals initial velocity in the y direction squared minus 2gh, like 2ax, 2gh, same idea. Right? Yeah. Throw it upward, gravity flowing downward. That's where the negative sign comes from. Okay, so we got all that. Okay. Oh, well, I know I threw the ball up at 30 meters per second. Square that. Okay. Minus 2 times, got 10 meters per second squared. And this h, I really want the maximum height point. So I'll go ahead and write that out, maximum height. Okay. Now if I do that, then that is going to correspond to only one final velocity in the y direction, which is how much? 0, exactly. Okay. This and this go hand in hand. If you throw a ball straight up in the air, at the maximum height point, it has 0 velocity. Right? In the projectile, that's also true vertically speaking. So at the maximum height point, yeah, it's moving horizontally, but that's not in the equation. The equation is only focused vertically, and vertically, it's not moving up or down. Aha. Okay, guys good? So let's try this out. Got 0 equals, I got 900 minus 20 h max. Throw some units on here. Meters squared per second squared, meters per second squared. I add this over to 20 h max equal to 900. H max is 45 meters. Oh, look at it. It's the same thing we got before. Is that exactly what we got before, right? So the old way, or using the first kinematic expression, say what's the height as a function of time? So, well, I know it'll peak at 3 seconds, so I'll go ahead and plug in 3 seconds. We got 45 meters up. Okay? The third kinematic formula, so well, I know at the top it'll be moving 0 meters per second. I can solve it that way. I still got 45 meters up. All right, you guys can do that? Are we good? All right. All right, so let's move on to how far down range does the ball land? What's this horizontal displacement x? Maybe I should label that on my diagram here. This whole horizontal displacement from the blast point to the crash point, I'll call it x. What is that x equal to? All right, oh, well, now we're switching over thinking horizontally, because we've been thinking vertically for a long time, because how fast was the ball going strictly up initially, and gravity field, those two together were constraining both how much time it would be in the air for at all, and also how high would the ball go, right? But now, how far down range does it land? That's a horizontal type question. Hey guys, for any of this horizontal motion on these projectiles, there's only one equation you're ever going to use. I bet some of you guys know what it is. It's very short. It's like 3 variables. What? Distance equals speed times time, like that. Right. I'm gonna throw a little subscript X on this V because it's just in the horizontal direction. Do you guys know this one before you ever walked in this room? We're going 60 miles an hour. I do that for 3 hours. I've just driven 180 miles. You guys can do that. It's just that. Okay. How many of you guys notice that this is true whenever you are not accelerating? Let me make that really clear with these expressions right here. You guys remember these 3 kinematic formulas? Right. What if I let this acceleration go to 0? Doesn't it knock out this term? And oh, look what you're left with. Distance equals speed times time. Okay. All right, what about the other ones? What if this acceleration goes to 0? Oh, well, the speed never changes. What about this third one? If the acceleration goes to 0? Oh, okay. Speed squared is still speed squared, or speed never changes again. Right, so maybe these bottom ones aren't very helpful for 0 acceleration, but this top one just boils down to that, doesn't it? Right, that's all it is. Right, that's this guy right here. So let's get some numbers in here. Get some numbers. So fast it was going for so much time. Ooh, guys, what number goes right here? How fast across the field is this ball going? 40 meters per second. 40, 40, 40, 40. It's always 40 meters per second, isn't it? I got 40 meters per second. Okay. And for how much time? 6 seconds. 6 seconds is the full time, right? Now, that we solved earlier, and that was related to its vertical motion and the gravity field. Okay, so that did take some work to get that, but we've already done that. So here, I'll go ahead. And it's 240 meters. That's the answer. What was that, about 2.5 football fields about? All right. You guys doing good? So I want to show you guys some posters. I'm going to kind of start at the end here because I got one poster that actually exactly answers this question. This looks pretty straightforward, right? Distance equals speed times time, right? But but actually, wait. This time was dependent on its vertical motion, right? You could make this a little fancier looking, right? Do you think, in principle, you could determine how far downrange a ball lands if all you know is how fast you throw it, or say the blast speed, if you know the angle from the horizontal and you know the gravity field, right? Can you just one equation shove it all in one go? Right? No, I haven't written out the full proof here, but I did show the end result. It looks like this. It involves this double angle identity. I want to show you guys that this does work for what we just got. So remember, guys, what was my full blast speed equal to? What was that? 50 meters per second. Watch this. Open parenthesis, 50 squared divided by what goes in for G? 10 meters per second squared. Right, close that parenthesis right there. Say times sine. Now I got this double angle identity. I'm going to talk about that here in a minute. Right. So 2 times this angle right here. Was that angle 37 degrees? Right, let's put it all together. See what I get. Oh, and before I hit enter, what number should pop up on my screen? We did everything correctly. 240. See if it does. 240 meters. Oh yeah, 240 meters. Oh yeah. Right. Let me modify that angle a little bit. What if it wasn't 37 degrees? What if it was 36.87 degrees? More in line with a true 3, 4, 5 triangle, right? Yeah, now it's even better. Here we go, 240 meters downrange. Guess that? Right. Right. So, where does this sort of come from? Well, it's kind of what we just did if you'd solved it all in terms of variables. And that double angle identity, I've been asking students today, do they know this double angle identity? I've been getting some blank looks. So let's see, does anybody here know this? Sine of a double angle, right? Like 37 degrees times 2 would be, oh, what what is that, 74, I think? Okay. Is equal to, can anybody finish this out? Does anybody know what this is? Who's seen this in a math class? Anybody seen this in a math class? No, I think maybe they don't teach us. 2 times sine theta times cosine theta. Okay. This has popped up a few times. I've used this, well, including here. It's like part of a larger proof. So that's just one step. Can be a handy one to know. All right, so you guys are right there. All right, let's look at some other posters though. Other posters. See what else I got for you guys. All right, so I got. Ooh, hey, look at this. I got a pair of posters that you guys just basically put in your notes. Didn't you guys just do all this in your notes? You guys just did all this, didn't you? Did all this. So there's 2 posters knocked out right there. Bam, done. In your notes. Right. Oh, hey, actually, we used this one near the beginning. If you blast at some speed at some angle, you can figure out how fast going across the field and how fast strictly up. That's cosine and sine. You guys do cosine and sine. Did that a few weeks ago, and also earlier today we did that. Right? Again, if there was no gravity field, it would just follow a straight line forever. But if there is gravity, maybe it'll start to bend down with the speed, your initial conditions, especially on that vertical. Also got, blast from the edge of a cliff. All right, so I'm getting closer to a lab I'm going to do with you guys. Yeah, here, I'll show you guys the lab equipment, and then I'll go back to the posters. Right? So tomorrow, I think I want to do this with you guys. Is take these launchers with it. So we got this launcher. You guys got some ramrods. You guys got some squishy bouncy balls. Okay? Now, you can take the ramrod and, guys, listen really closely. Listen. You guys hear it click? Okay? Now, that's short range. Let's go next one. That was really ready to go. It's medium range. Wait, what's this? Long range. Notice, guys, did I put in the squishy bouncy ball first and then start ramrodding it? No, because you think this would get like mashed in there and then it would get jammed, and then that would be no fun, right? Notice I ramrodded it first, and then I'm going to put the squishy bouncy ball in. Okay? And you guys do the same thing tomorrow, right? Then all I got to do is lift this lever right here and watch this. Oh, out flies that squishy bouncy ball. So tomorrow, I think I want to take you guys to the balcony. Thank you. Okay. And we set this up on the balcony, right? And aim it horizontal, pow, let it fly out. And it's going to follow that parabola right there. And you know it's a parabola because look at this. You guys see that horizontally, these are evenly spaced. Okay? But right? Gravity doesn't pull horizontally. Gravity only pulls vertically. Right? And then air drag is probably tiny, like negligible. Right? But look, vertically, it's a different story. You can see it's getting like more and more spaced out vertically, like every successive time interval, every second. Okay. How far does it go horizontally? X equals vt. How far does it go vertically? Hey, 1/2 gt squared. Does that look like the college equation? Right? It's been falling for 5 seconds. How far? About 125 meters. How did you know that, college? That's that one right there. Right? That's the college equation. Is it? Right, now, what can we do with this? What can we do with this? Let's put this together. One thing you could do with this is you could figure out, if you knew the blast speed, do you think you could figure out the blast distance? That would go like this. The time of fall would be constrained by the height of fall and also the gravity field. You could solve for the time of fall. Hey, where have you guys seen this? Just this bit in Reading right here, which is all the vertical stuff is in Reading. Right? Is that the lab you guys did where you held a ruler and you dropped it and your friend caught it? It's like, I caught it at 18 centimeters. And I can calculate my reaction time. That's that right there, isn't it? If the ball's been falling off that balcony, if I give you guys a meter stick, you measure how many meters tall that is. You can calculate the time of fall, right? And then if you knew the blast speed, could you just very quickly multiply by that time of fall and then get the total blast distance like this right here, right? Now, I'm not quite going to have you guys do that tomorrow. I'm going to have you guys do a little bit of variation on that, which is kind of a similar question, just backwards, right? I want you guys to calculate the blast speed based on the fall distance and the landing point distance, right? So all the vertical information in Reading, okay, this is the same as what you guys just saw, right? Hey, there's the fall time. It's square root 2 h on g, just like I did for my reaction time lab. It's the same thing, right? So you've done that already. Okay? Right? But now it's going to finish off a little bit different. Right? Now I want to solve for blast speed. Well, I know that the blast speed is the horizontal speed, so it's going across at constant speed. So that's how far it goes, d divided by how much time t. And that time t is going to be, well, you can calculate it using this here. If you guys want to calculate numbers along the way, it looks a little easier than those two, right? So if you know it falls so many meters in such and such gravity field, like, okay, I can solve for so many seconds of falling and say, okay, well, I know it went so far, it fell in so many seconds, and just divide those out. You could do that, right? Boom, boom, and then you get it, right? If you want the answer in terms of variables, this is it all put together in this black ink right here. That's how it works out. Okay. Boom. All right. All right, so you guys set so far? Right, guys good? All right. Since we got an extra minute about in class here, this is about where the bell's been ringing in my other classes, but I know this one we got an extra minute. Right. Let's take a look at this real fast. So just to look at the organization page, hopefully you guys have read some of these. I gave you guys 1, 2, 3, 4, 5, 6 different projectile scenarios. Some of these involve blasting a cannon horizontally off the edge of a cliff, just like the poster I was just showing you for the lab setup tomorrow. And some of these involve cannonball firing on a plane at some angle. Oh, that's what we've been doing most of class today, right? Or maybe you start by sine and cosine components, and then you solve some stuff there. Right? I gave you some information. If I give you enough information, you can solve everything else. Right? Then on the back side of this are, maybe a little bit more complex, where you have both put together. I got a cannon on a cliff, but also it's angled at some angle. Wow. Okay, so yeah, but I lead you through step by step. So first find the components and then solve for, hey, look, and I gave you guys some multiple choice too. So that's kind of nice. Right? All right, so let's get a quick glance at that paper. I do want to solve a bunch of these with you guys in class, but we're gonna have to save those for another day. That's gonna be our pause point today.